Yeah, I got some.
We can hear you, Marco.
I'd like to welcome you all to this week's Astrobiology seminar. We're very pleased to have returning to the fold one of our own, Sean Raymond, who was got his PhD in the astronomy department here and was also an affiliate of the Astrobiology program. An affiliate through design, not choice, because I think you were sort of a bit too far on in your PhD program when astrobiology started. But we count him as one of our most successful products, even though he probably doesn't count us as one of his most successful mentors. But we're very proud of him. So Sean's doing a NASA postdoctoral fellowship at the University of Colorado, and he's going to talk to us today about exotic Earths.
Thanks, Roger. All right. You mind hitting the lights there? All right, so it's a pleasure to be back in Seattle. Thanks for coming to my talk. What I'm going to be talking about today is I'm going to talk about some things that are kind of related to the formation of habitable planets, kind of like Earth, but I'm going to talk about a few cases, kind of a few systematic things that people don't usually talk about, which actually play a really important role in terms of what Earth-like planets might look like, in terms of their water content, in terms of their size, in terms of where they could actually exist. So for example, here's another, a planet that might be habitable, a planet that's actually in a hot Jupiter system. So we're an ocean-covered planet, the sun's just setting, and we got a hot Jupiter right there. And so this is the kind of planet that we think might form, quite often around other stars. And I'll kind of talk about why that is and where they come from. So before I get going, I want to acknowledge my collaborators. There's lots of people who kind of helped me with this, with all the stuff I'm going to talk about. Lately, I've been doing a lot of stuff with Rory Barnes and Eric Gaidos and these guys, but all these guys contributed to what I'm going to talk about. And I always have to thank NASA Astrobiology Institute for funding. They've been funding me for the last 5 or 6 years or so. So thanks to them. So here's a little outline of the stuff I'm going to talk about. First, I'll give you kind of the standard picture, which is kind of the normal picture of what we think of how habitable planets like Earth are thought to form. And then I'll talk about these weirdos, kind of 3 weirdos. I'm going to talk about 3 weird stories, probably 10 or 15 minutes each. I'll talk about aluminum-26, which is a short-lived radioisotope, which is present in the solar system. We have evidence from meteorites that it was alive in the solar system in the early stages of planet formation, and it might play an important role around other stars. Then I'll talk about hot Jupiters. Those are gas giant planets very close to their stars. We think they formed further out and migrated in. And so I'll talk about whether habitable planets can form in those systems. And then I'll talk about low-mass stars, about whether habitable planets can form in those systems. And actually, for many low-mass stars, planets that are in the habitable zone would have significant tidal evolution. And I'll kind of mention that a bit. So here we go. Here's the standard picture of how habitable planets form. Here's a little cartoon version of what we think is going on. Start with a molecular cloud. Little piece of it collapses. You get a disk. And from that disk, the solar system forms. So that's the very nice overview picture of what's going on. I'll give you a little more detail in a sec. All right, here's kind of what we think the Solar Nebula, the protoplanetary disk that formed the solar system, what it might have looked like. It's kind of hotter, closer into the star. And so kind of the species that are available to build solid planets depend on the local temperature, which in turn depends on the location. So very close to the star, planets typically form from refractory things like metal and rock. Further out, they can form from things like ice and, in more volatile species. And this kind of evidence from this kind of process, hotter closer in and cooler further out, is seen in terms of the water content of primitive meteorites, which we think are tied to classes of asteroids. And so how do planets form in these kind of disks? Well, there's a bunch of different stages. I'm not going to go into detail into most of these stages. We start off with kind of grains condensing to a thin plane in these disks. From these small grains, you form kilometer-sized things. And this step number 2 is kind of the one that's the most uncertain right now. Lots of people are thinking about how that really happens, how you get these kind of kilometer-sized planetesimals to form, because these things are really the building blocks of Earth-like planets. The next stage is the formation of larger things, maybe Moon or Mars-sized things that we call planetary embryos. And this picture right here is a snapshots from a simulation of that third stage of what's called oligarchic growth. And so you can see these little guys are forming, are accreting to form larger bodies, these moon-sized things, which you have down here. And they tend to form with kind of a characteristic spacing. They tend to form with more or less a characteristic mass. They tend to form closer in faster. And this stage where you have just kind of a relatively small number of these large guys lasts until the amount of mass in the big guys and the small guys is about equal. And when that happens, kind of these feeding zones overlap and you end up having collisions between planetary embryos and kind of this final stage of growth of terrestrial planets. And a key thing to make note of is that gas giant planets form pretty fast. They form in maybe a few million years or so. We know that because that's how long disks of gas are present around other stars. So the gaseous planets have to form while those disks are still around. So those gas giant planets probably form faster than terrestrial planets. So this final stage, especially the stage 4, called late stage accretion, which is this final sweep up of planetary embryos and planetesimals, probably happens in the presence of any gas giant planets that formed in the system. So here's a little movie of that happening. So in this movie, we're looking at distance from the star. The star's here at 0, orbital eccentricity on the y-axis, and the temperature has kind of imposed a water structure here. So close into the star, things are dry. That's what red is. Further out, they have more water. Out here, they have 5% water by mass. And just off the screen is a Jupiter-sized giant planet that's not explicitly shown here, but you'll see its effects in a second. So what you're going to see straight away is a few vertical lines at certain distances, and what those are mean motion resonances with the giant planet. So here we go. So boom, there we go. This was the 3-to-1, this was the 3-to-2, and 2-to-1, but they get smeared out pretty quickly. You can see planets are forming faster, closer in, close to the star, and slower further out. And you can see after 5 or 10 million years, this guy here is about an Earth mass, but he's still completely red. He still doesn't have any water, so it's still pretty dry. But then as time goes on, more mixing happens between these different zones, and by the end of the movie, or even by about 20 or 30 million years, this guy here, which will be kind of the Earth analog in this case, has a good amount of water. And these zones keep mixing, and you end up with, in this case, 3 terrestrial planets form. This guy right here at 1 AU is more or less like the Earth, and you can see that there's an asteroid belt that's kind of slowly getting cleared out there. Let me stop this before it finishes. This guy looks a lot like the Earth. It's about the same mass as the Earth. It's about actually 2 Earth masses or so, but it's about the same orbit as the Earth. And this is kind of the standard picture. This is how we think habitable planets form. This guy got some water by accreting material that originated further out, and so it can be in the habitable zone and have the right temperature for water to be liquid on its surface, and also have gotten some water by mixing between these different zones. So this is kind of what we think is going on.
What about its eccentricity bopping back and forth? Does that continue?
Mm-hmm. Yeah, that's kind of a typical thing. That happens. The Earth right now, today, the Earth's eccentricity, for example, oscillates between about 0 and 0.06 or so on a time scale of, I think it's 20,000 years or so. And so that's all the planets in the solar system are currently having eccentricity oscillations, and you could see that explicitly in the movie where the planets were kind of bopping up and down a little bit. So that's kind of the same kind of thing that's happening in the solar system right now. It's just happening really slow, so we can't see. And so what happens if you do a bunch of these models is you can see there's a lot of diversity in terms of what terrestrial planet systems might be out there. In this case, there's 11 simulations that formed a planet that was in the habitable zone at around 1 AU or so. And then the solar system is here for scale. And so you can see there's a lot of diversity between the actual systems of planets themselves. For example, this guy is just a 1 terrestrial planet system, whereas this guy's on the opposite end of the spectrum, has 7 or 8 planets that are Mars size or larger. And for example, the actual planets that are in the habitable zone have a lot of variety as well. They range from these really big planets that have a lot of water to ones that look a lot like the Earth, like these guys, to ones that are in the habitable zone but actually have not accreted much water. And so there's a lot of variety out there. And these are, the variety we see here, these are all for systems that have very similar starting conditions. The starting conditions were slightly different here and there, but more or less the same starting conditions. And so if there's this much variety in terms of outcomes, for more or less the same starting conditions, then for much different starting conditions, there's probably exponentially more variety. And what is it that really sets this variety? There's kind of two factors that are important for the differences between planetary systems. One is just stochastic noise, which is kind of a random effect. When you go from a large amount of bodies to a small number, towards the end of that process, individual scattering events become important for the outcome. So if things are just a tiny little bit different, you can have quite a different outcome. So that's kind of the random factor. And then in addition to that, there's systematic variations. And there are two kind of key parameters that determine that. The first is simply the disk of stuff that the planets are forming out of. You change the disk the planets are forming out of, you change the planets that form in the disk. It's pretty simple. For example, a higher mass in the disk, if a disk has more mass, it'll tend to form a smaller number of planets that are more massive. And why is that? It's simply because the eccentricities get excited more when you have a disk that's more massive, and so feeding zones tend to be a little bit wider, and so you can sweep up more mass. A given planet can sweep up more mass. And it also depends on, for example, the surface density profile of the disk. And giant planets, like I mentioned, form in these disks also and influence the final phases of terrestrial planet formation. And so, they affect, the outcome as well. So, all right, so that's it for the standard story. Now we're going to move on to kind of other effects that deal with this planetary habitability stuff. So I'm going to talk about three effects, and in a little cartoon they kind of fall in different places. So the Illumina 26 story falls early on, while the sun was still or stars are still in embedded clusters during the first 10 million years or so. So I'll talk about that one first. Giant planet migration happens in these disks around stars. It relies on interactions between planets and disks. And for M stars, I'm going to talk in particular about tidal orbital effects, which happen over billions of years. So they happen after the system is completely formed, just over long time scales. So first off, we'll talk about the Illumina 26 story. And so this story is linking kind of what we see in meteorites, tells us something about the content of planetesimals in the early solar system. That in turn tells us something about the birth environment of the sun. And then by looking at, by imagining clusters of stars that form, stars like the sun, which eventually form planets like Earth, looking at different stars on different orbits within the same clusters, we can say something about what planets, the composition of planets in stars like the sun, but who had slightly different orbital histories within their cluster. So that's what we're going to get into. So to start off, there's evidence from primitive meteorites for live aluminum 26 in the early solar system. And so in this plot, what we're looking at is we're basically looking at a different isotope of aluminum, normalized by isotope of magnesium, versus the daughter product of aluminum 26, which is a heating element. And basically this correlation is interpreted as evidence for live aluminum 26 at the time of formation of these minerals in this primitive meteorite. And so we think there was live radioactive stuff, in these rocky bodies at the time of their formation. And there's evidence for other ones besides just aluminum 26 that were in the Solar Nebula as rocky things were starting to form. There's evidence, for example, for beryllium-10, aluminum 26, so on. There's actually many more of these. And it's been debated where these things come from. There's a couple different ideas. The kind of two competing ideas, the two main ideas are either kind of a local source versus an external source. And the local source is just it's solar energetic particles coming from the sun interacting with the disk can actually create some of these short-lived radionuclides, locally in the disk. The trick is that would kind of imply that they shouldn't be homogeneously distributed within the disk. They should be concentrated kind of towards the inner regions where they're actually being formed. And it turns out there's some evidence to suggest that they that the radioactive stuff was actually pretty homogeneously distributed. And so that's kind of some evidence against this idea. It's not completely shooting that idea down, but there's some evidence against it. The idea that I'm going to go with is that the short-lived radionuclides came from massive stars, both from winds from massive stars and also from supernova ejecta. And so iron-60 is actually kind of the smoking gun for a supernova having produced that isotope that ended up in the Solar Nebula, because you can't be produced locally like some less massive ones. And so so if the radionuclides in the Solar Nebula came from a massive star, that actually requires the sun to have formed in a pretty big cluster. Why is that? Because of the mass distribution of stars as they form. Most stars are very small, puny things, and to form big things like the OB stars, what they're called, these very massive stars that end up going supernova and polluting the rest of the cluster with these radionuclides, you need kind of statistically a certain number of stars before you form one of these big ones. And so actually it turns out that the most likely mass for the cluster, or the most likely number for the amount of stars in the birth cluster of the sun is something like 10,000. So since we have evidence for this stuff that was injected, we think, by a supernova, the most likely cluster size is actually the size of about 10,000 stars or so. And so that's kind of some indirect evidence for the sun's birth environment. And so the sun was born in some kind of place like this. This is the Orion Nebula. The sun was actually born in a place much bigger and less wimpy than the Orion Nebula, with a lot more stars, something like 10,000 or so. So that's kind of neat.
Sean, how short-lived are these?
Okay, I have a big table that I could show you with all the details of all this. They tend to be the half-life tends to be about 1 million years or so. The one that I'm going to talk about the most, Illumina-26, has a half-life of 700,000 years. So they're short-lived in terms of like the crossing time of the cluster, for example. So they have to have a relatively local source within the cluster. All right, so how do you get these short-lived radionuclides from high-mass stars? Well, most stars are thought to actually form in pretty massive clusters, with thousands of other stars. And these massive clusters contain, massive stars. Just statistically, most stars are wimpy, like I was saying, but a few of them are really big. When you have a very massive cluster, then you tend to have a few of these really massive stars that tend to actually be more or less at the center of the cluster. And these are the massive stars that create the short-lived radionuclides and can pollute nearby stars with this material. And so here's kind of the general picture we have of what's going on. Is that, one of these large, massive stars has various phases where it goes through like this Wolf-Rayet wind, for example, and then supernova ejecta, and nearby stars can be polluted with that material. How does that actually happen? Well, here's a model of what's going on inside a star. So you can see the age of the star in millions of years there versus its mass in solar units. So a 60 solar mass star kind of loses mass there. Then during this phase, what's called the WN phase, it has very strong winds. It's during that phase that most of the Illumina-26 is created. And it's not till the very end that you get the spike of iron-60 in the actual supernova. And how does that end up in a disk like the Solar Nebula? Well, what we think happens is that you have this shock front. When you have this wind from the massive star coming from the right, a shock front is built. The gas kind of flows along these lines, but actual grains, which contain much of this, very refractory stuff, these radioisotopes, can actually get injected directly into the disk. The grains can pass through the shock, whereas the gas can't. So this is kind of the general model for what we think is going on in terms of how this radioactive stuff gets into another disk. And so the picture there is similar to, for example, this is a little peroplet in Orion. This is an observation, and you can see the disk right there. And this kind of shock is the kind of thing that we think, this kind of picture we think is more or less what's going on here. Although in this case, it's not supernova ejecta that's happening, but this kind of, object is really out there, and we think this is what's going on. So like we mentioned, there's kind of a delay of a few million years within a cluster before you can pollute it with these short-lived radionuclides. And the reason for that is simply because once massive stars form, they don't go off as supernovae immediately. they take a few million years, like we saw before. And so if you kind of simulate a star cluster with about 10,000 members or so, and then track the orbits of all the stars that are like the sun, and see kind of, in this cluster, there are actually, in this case, 3 massive stars that go supernovae, and kind of keep track of how much, in this case, aluminum-26 ends up, being embedded in that disk, kind of in a relative sense, because it's difficult to calibrate in an absolute sense. But in a relative sense, then you get kind of this curve. And so the relative abundance of aluminum-26 in a cluster of about 10,000 members, which is a typical cluster in where a large fraction of stars are formed, the distribution of these short-lived stuff more or less goes like this. So it's kind of, in this case, it's peaked around some nominal value, which is actually pretty close to what we think is the value for the solar system. And then there's a tail of stars which got more radioactive material. There's probably something like 5 or 10% of stars got more aluminum-26 than the sun. Then here, some fraction got less, and actually a large fraction, something like 50 to 80%, aren't even on this plot, because by the time the supernovae went off, they weren't actually part of the cluster anymore. So a lot of the stars aren't even shown on here at all, because they were already gone. And so what actually happens there is that the gas is holding these little embedded clusters together, and when the gas dissipates, the whole cluster kind of falls apart. And the cluster is slowly falling apart during that process. And so, a good chunk of those stars never got any of this aluminum-26 at all. And so why do we really care about this aluminum-26 stuff anyway? Well, the reason is that aluminum-26 heating is thought to have been really important in kind of small bodies, maybe kilometer-sized bodies in the solar system. For example, the distribution of S versus C class asteroids can be explained by heating, but actually I'm getting ahead of myself. In this plot here, for example, what we're looking at is the accretion time scale of bodies, so up to 20 million years there, and these curves are showing how much mass did not get heated up that much. So it's a little bit backwards. How much stuff didn't really get heated up that much as a function of the time it takes them to form. And so in green is the solar system's worth of aluminum-26, and blue is 10 times less, and orange is kind of 10 times more aluminum-26. So what does this mean? Basically, you get, for a given kind of formation time, if you have more of this aluminum-26, you heat up a whole lot more material to high temperatures, which tends to get rid of all the volatiles, especially what we're concerned about here is water. So it's a balance between the half-life of aluminum-26, which is 700,000 years, and the formation time of bodies. So, like I was mentioning before, these S versus C class asteroids. S class asteroids are tied to ordinary chondrites, which don't have that much water. C class are tied to carbonaceous chondrites, which have maybe 10% water. And the break between the two happens at about 2.5 AU or so. And that's explained by the formation time. Like I mentioned before, it takes longer to form things further away from the star. You're kind of racing to form things versus the decaying aluminum-26. And that's why you have dry things here and wetter things further out. And so this division, which was at about 2.5 AU in the solar system, is obviously a function of how much aluminum-26 you have. So for example, here's the position of that division between wet stuff and dry stuff versus the relative abundance of aluminum-26. And there's some uncertainty here because we don't know exactly how long it took to form things at a given distance. And so these three curves are for different formation timescales at 2.5 AU. But in general, if you have more aluminum-26, then the division between dry stuff and wet stuff is further out. It's not exactly known where it is, but it's further out. And for that large chunk of systems that didn't get any aluminum-26, it's closer in. And what does that mean? Well, before we were looking at, planets like Earth forming and needing this mixing between zones to get water onto a planet. And so if the region you need to mix from is further and further out, then it's harder to get water on there. So for example, here, here's the average results of about 30 simulations that are designed to replicate the solar system, to reproduce Earth. And so, what we're looking at here is the water content versus the location of that division between dry stuff and wet stuff. And like you'd expect, when that division is closer in, it's much easier to get water on planets. And so you could have planets with maybe 10 times more water than Earth. If there was more aluminum-26, that division's further out, then you probably get less. Okay. And so the general punchline of this piece of the story is simply, depending on the birth environment of a star, you can be closer or further away from a supernova. You can get more or less aluminum-26. And so say you get less, that means the division between dry stuff and wet stuff in the disk stuff that you're forming would be closer in, and you'd end up with wetter terrestrial planets. So that's part one. All right. Part two, hot Jupiters. All right. Can habitable planets form with hot Jupiters? Okay, so giant planets are all thought to form kind of further away from their stars. There's different lines of reasoning for that. So we think giant planets form kind of out here where Jupiter is. However, lots of them are observed really close in. So what's going on there? Well, we think what's happening is they form further out, they move inward and become hot Jupiters. And so during that process, they're migrating right through this zone where planets like Earth are trying to form. And so a key thing is, can you still have planets like Earth given that this is happening? In those kind of systems, can you still form habitable planets? And so people have argued about this in the past, obviously. So previous results, there's some no just kind of by assumption. If a giant planet's migrating through this region, you can't form little puny rocky planets. Some people have thought that. Some people say, no, if, waving your hands this way, then you can say, yes, if this is happening, or yes, if that, Basically, it's time to look at this in more detail. So that's what we did. So, all right, key things, in addition to just gravity, which was included in those previous calculations, like that previous movie I showed you, here we had some new stuff. For example, we included the effects of type 2 migration. This is migration of a giant planet which is embedded in a disk. It's massive enough to actually carve a gap, an annular gap in the disk. That happens when the giant planet's kind of region of influence is larger than the scale height of the disk. And then the giant planet ends up migrating inward on a time scale of maybe 100,000 years or so. And we also included the effects of gas drag, which are important especially for smaller bodies. Planetesimals have their orbits recircularized pretty quickly by gas drag. And so that's important to include as well. And so here's another movie. What we have here is the same kind of thing as before. The different colors represent the same thing as before. Red is dry, blue is 5% water. This guy right here is a giant planet that we're going to migrate through here. And notice that we're on a log scale now, just so you can kind of see what's going on very close to the star. Where's my mouse?
Now, Sean, you haven't said what the basic cause of the migration is, I believe.
Okay. I didn't want to go into much detail with this. But what causes the migration is basically the planet, when it carves a gap, becomes tied to the evolution of the disk. What the disk does is most of the disk viscously accretes onto the star. So as it kind of is falling onto the star, it drags the planet with it. And that's what this type 2 migration is. It doesn't always have to go inward. In some cases, it could actually go outward. But for hot Jupiters, it's thought that that's what's going on and moving inward. All right, so here we go. The hot Jupiter is being moved inward. So what's going on? We're plowing through all this rocky stuff. These vertical lines are specific resonances, mean motion resonances with the giant planet. This is 3-2 and 2-1. You can see about half the material will end up being pushed inward by the giant planet, and about half will end up being scattered outward on these high eccentricity, high inclination orbits. And so it's kind of neat. You can see things, as before, things are forming pretty quickly in there. And then some of them are just getting chucked out. They're being shepherded here by the giant planet. But if by chance, their orbits aren't quite aligned right, then they can have a close encounter, and that's when they get chucked out. But in the end, about half of that total disk material ends up being pushed inward, about half chucked out, and a surprisingly small amount actually hits the giant planet. And so the real question here for forming planets like Earth, there are 1 AU, so can this scattered stuff form another generation of terrestrial planets? That's the real question. And so to address that, we have another movie. And in this case, same thing as before, but instead of only going to 100,000 years, this one's going to go for 200 million years. And we're also including an extra component of kind of cometary type material, which starts off exterior to the giant planet. And like I mentioned, because of interactions with the gas, some of this stuff can actually spiral inward a little bit. And that'll be important. So, the migration happened really fast here, right, in 100,000 years. And then the stuff got all scattered out here. You can see it's the mixing between zones is really big. It's kind of like a rainbow out there. After 10 million years, everything's going to go nuts, because that's when the gas dissipates. The gas was damping the eccentricities of the planetesimals, which were in turn damping eccentricities of larger things. And so, let me stop this guy before it's completely over. All right, so this is more or less the end of the movie. So what happened is, interior to the giant planet, we got this, we call it kind of a hot Earth planet. It's rocky, and it's very close in. It got shepherded in front of the 2-to-1 resonance, in this case, with the giant planet. Exterior to the giant planet, all these things had really high eccentricities, really high inclinations. In time, they got decreased to some degree by interactions with the gas. And the key thing is mixing between zones that we need to get water onto planets is really, really strong. Because all these things had really high eccentricities, so mixing was very vigorous. And so this planet right here that formed at about 0.9 AU ends up with something like 20 times as much water as the Earth. And that's not 20 times as much water. That's basically 20 times as much water compared with other simulations designed to reproduce the Earth. Because we still don't know exactly how to account for water loss during large collisions. That's kind of a tricky thing. But, this guy has about 20 times more water than cases where we kind of reproduce the Earth. So we think this guy really has a lot of water because of how it formed. And what does this look like? Well, this is, how we started. Probably looks something like this. Ocean-covered surface. It's just at sunset, which is a really nice time for these kind of pictures. You got the hot Jupiter there. Even closer in, there's a little flip. That's that hot Earth planet. On Earth, storms tend to get really big over water and kind of peter out over land. So if you got no land, maybe you'd have really big storms. But the storm can't block the view, So it's just, the storm front is just coming in just now. It's just perfect. And could you have any life on this planet? Well, who knows, of course. But we went ahead and drew some, some kind of crazy beast in there. And I had to throw in one more joke from my thesis. This is another possible scene from one of these planets. There's a famous movie called Waterworld about this. And you got to go hunting and such, so that's what you eat on these planets, these crazy beasts.
John, you had the gas dissipating in the last one. Was that just something you imposed, or is that something that naturally comes out of your model?
We imposed that. Yeah. So observations.
In fact, that we see that in other stellar systems.
Yeah, observations suggest it takes like a few million years to disperse the gas. In this case, we went for 10 million years, which is kind of on the long end. But yeah, we dispersed it, and exactly how the gas disperses is not really well known. Whether it's exponential. In real life, it's probably some kind of exponential, but with a step type shape due to kind of nearby stars.
With time.
Periodically periodically photoevaporating a lot of the disk. And so we kind of had a linear decay, but it doesn't matter too much. It doesn't really affect what's happening exactly how the gas dissipates. Oh, yeah, go ahead.
What assumptions about water retention do you implement?
Oh, in that case, everything was retained. And so that's obviously not realistic, and that's why we compare the outcome with other simulations rather than with the Earth directly. Mm-hmm. Okay, so I mentioned that with the migration you can form lots of these close interterrestrial planets. So for example, here's 9 cases where this is the giant planet that got migrated into here, and here's the hot Earth planets that formed. And they tend to form, have been shepherded by maybe the 2-to-1 resonance is the most common, kind of shovel that pushes these things inward. And the masses in these cases tend to be something like a few Earth masses total. But that will depend on the disk mass, because typically about half of the solids in the disk end up being pushed inward. And actually in this case, very interestingly, if the giant planet here, if each of these were orbiting a star, a distant star, and if each of these giant planets were transiting its star, and you were to look in kind of deviations and the timing of transit from a perfect chronometer, stuff like Eric Agol and Jason Steffen are doing, then these planets would actually be detectable. They would have a big enough signal in terms of the deviation of the timing of the giant planet transits that you could detect or infer the presence of these extra, rocky planets. And so that's kind of neat. That's one other way besides, a more direct method to actually find. And one other thing you can do here is kind of extrapolate these results to try to figure out, based on these formation models, which of the known giant planet systems could have planets like Earth. And I don't have much time to talk about this, so I'm going to kind of skip over it quickly. But the only thing I want to point out is that kind of a neat thing is that on this list that we made before this thing was discovered, was we kind of said, the star Gliese 581 is one of these candidates that could maybe also have a planet in the habitable zone. And we're going to be talking more about that star in a minute. So that's the end of story number 2. Now on to story number 3, talking about low-mass stars, the prospect for habitable planets around low-mass stars. So first of all, what's different about low-mass stars that's not the same as high-mass stars, or normal sun-like stars? Well, obviously they're faint. The luminosity of low-mass stars goes down with the stellar mass to about the 3 or 4 power, which means a few things. It means that the habitable zone is very close in. Right, the region where you're getting the same amount of flux from the star is closer to the star. And what that in turn can mean is that tides are very important. So for example, here this plot is showing stellar mass versus, the location of the habitable zone for different stellar masses. And it's a log scale, so it's 0.1, 0.2, 0.3, 0.4, up to 1 solar mass. And so this shaded region is the habitable zone. And this dashed line represents the limit of where tides are important. So in here, tides are important. Now here, they're not so important. And these little different shadings here are estimates of the habitable zone for different amount of cloud cover that are doing slightly different things. Clouds out here that could be warming, or clouds here that could be cooling to some degree. And I'll talk more about that in a minute. One other thing that's important is that the mass in protoplanetary disks seems to scale about linearly with the stellar mass. But, on top of that, there's a very large scatter. And so typically lower mass stars will have less massive disks. Although in every case that doesn't have to be true on an individual basis, but in general that's the case. So, given that there's less stuff statistically for low mass stars to build habitable planets, and the habitable zone is so much closer in, where actually the zone in which there is material is smaller, means that the kind of typical mass you would expect for planets in the habitable zone, if they're forming kind of right in situ, is smaller for low mass stars. And so this plot is showing kind of stellar mass, the typical mass in the habitable zone. It drops pretty quickly from 1 Earth mass is where we calibrated for 1 solar mass, down, and it gets very small pretty quick. And there are various hand-wavy limits you can put on how massive a planet you need to have life, and those tend to fall kind of in this shaded area. So either way, for whatever limit you choose, for low mass stars, the prospects for having a planet that's massive enough to be habitable are less. And so this leads us to think things that habitable planets around low mass stars might be rare, just because you won't be massive enough to have things like plate tectonics or a thick atmosphere and that kind of thing. And of course, right after we were doing this kind of research, the first maybe habitable planet was found around an M star, so it felt very clever. Anyhow, so this is this star called Gliese 581. It was discovered in April of this year, and there are 3 known planets in the system with masses or minimum masses between 5 and 15 Earth masses. And Roger was just mentioning that there was something on the BBC that they might have found another planet in the system, which I don't know about, but that's pretty cool. I'm just going to talk about what we can say about these planets without knowing if there's another one, but who knows, there could be more planets in the system.
It's better than Fox News anyway reporting.
Yeah, right. That's a good sign. All right, so the planets that are of the most interest are kind of the second and third planet out. And so here is the Sun, basically the planets in the solar system, and the planets in this other system, Gliese 581, kind of shown to the same, more or less the same scale temperature-wise. Okay, so this planet C was initially announced to be in the habitable zone, but it turns out it's not. It's even hotter than Venus, really. It gets about 50% more flux from the star than Venus does. And so it's probably too hot to be habitable now. Planet B is very close in, so that one's probably not habitable. This other planet, Planet D, is kind of at the outer edge of the habitable zone or so. And so maybe that one's good for habitability. We're not really sure. So a key thing is that tides are actually important for these two planets. And so we're going to look at the effects of tides on those planets. So tides can actually change the orbit of the planet. So how does that happen? What happens is a planet actually has to be an eccentric orbit will have a tidal. Any planet that's orbiting a star can have a tidal bulge raised on it by the star, and actually the star actually can have a bulge raised on it by the planet. But that's a much less important thing, and rarely actually affects the orbit of the planet. These tides end up dissipating energy and can actually cause orbits to move inward and tend to become more circular. And to have this happen to a large degree really requires some kind of eccentric orbit. So this picture is kind of showing the general idea. The difference in gravity across this planet due to this star is such that there's a stretching force. A point right here is drawn inward. This point, is drawn towards the center of the planet. This point is drawn towards the star. And relative to the center of the planet, this point here is drawn away from the planet. Or away from the star, And so the planet itself is getting kind of squished apart. And so what happens on long time scales is that if you have an eccentric orbit like this, the degree to which the planet is deformed, varies over the orbit. And on long time scales, the orbits tend to move inward on average and become more circular. Okay, that's the general process that happens. And the degree to which that happens depends on things like the size of the planet, because that'll determine the amount of deformation that can happen, and things like what's called tidal dissipation parameters, which deal with the internal structure of the planet and how well it can actually retain a tidal bulge over time. Okay, and let me just kind of jump on a different boat for a second. Since this requires eccentric orbits, then what does the habitable zone mean if your orbit is very eccentric? Well, one way to look at this is that climate models for the Earth suggest that the key thing to maintain a nice environment on the Earth is not necessarily the exact orbit, but rather kind of the orbit averaged flux. So the amount of flux that the Earth gets over a full orbit. And so that means basically the orbit average flux changes a bit with eccentricity, but not that much. You can calculate it. It changes a little bit such that at large eccentricities you get a little bit more flux if you're at the same semi-major axis. And so what does that mean? What it really means is that for very eccentric orbits, the habitable zone is actually a little further out. And so this plot is showing kind of the location of the habitable zone as a function of eccentricity for a fixed solar mass, a stellar mass of in this case 0.18 solar masses. And you can see it's more or less constant out to eccentricity of 0.6 or so, but then it gets a little bit further away for higher eccentricities. So now tying this to that planet Gliese 581c. Okay, so what we're doing here is looking at that planet Gliese 581c, the one that's just past the inner edge of the habitable zone, the one that's a little bit hotter than Venus. And what we're going to do is we think we know more or less how tidal orbital evolution works. And so we're going to rewind the orbit of that planet, given we don't know a lot about it, and so we have to kind of make different assumptions about what's going on that planet. But we're going to rewind the orbit of that planet and see if in the past its orbit might have been habitable. So it's not habitable now, it's hotter than Venus, but maybe in the past, since its orbit has progressively been moving inward, maybe in the past its orbit was further out and maybe it was habitable then. And so what we're looking at here is kind of looking back in time at the orbit of that planet, the orbital distance of that planet, for three different assumptions about the size of the planet. Okay, so in this case, the planet would be very large. It would be water-rich, probably. And in this case, the planet would be very condensed. It's very small, and the tidal effects are actually a little smaller. And so you can see these are kind of the black line shows the orbit rewound of the planet. And the reason these gray lines, which are estimates of the habitable zone for different cloud covers, are moving is because of what I was talking about the eccentric habitable zone. As these planets are rewinding in time, their average distance is moving out, but their eccentricity is also getting bigger. And so the habitable zone is actually moving out. And so, they're trying to, in some sense, they're approaching the habitable zone, but the habitable zone at the same time is moving further out. And so you can see is right now, if this planet had 100% cloud cover of clouds that were doing just the right thing, then there's a chance that it could be habitable. But it would need complete cloud cover. In the past, if it's a relatively large planet, then in the past it could have been pretty close to being habitable. It would have required much less clouds to maintain the right temperature. In none of these models does the orbit actually go into this dark gray region where it's pretty certain that it's habitable. But it's pretty close. There's a decent chance that this planet could have had more habitable conditions in the past. The trick is you can't just look at that one planet. Oops, I forgot about that part. Here we go. So the trick is, first of all, how far back in time do we need to go? Well, that depends on the age of the star, right? So we want to go back until the system was formed. But for that, we need to know the age of the star. It turns out it's really tricky to nail down ages of stars. In this case, the star is older than 2 to 3 billion years. And some people think that it might be as old as 8 to 10 billion years based on its very low X-ray flux. But statistically, this relation that X-ray flux decreases in time is true statistically, but it's not always true for each individual one because there's some scatter in terms of how much there is. So we think the star might be quite old, so we might have to rewind the orbit for up to 10 billion years or so. But it turns out that planet's not in isolation, it's in a system of planets, and so we have to look at interactions between planets as well. So here we're looking at that planet we were talking about, planet C rewound in time, and then also planet B. And the third planet is way out up there at about 1/4 of an AU. And so in the most kind of optimistic model, this planet was going back and being very close to the habitable zone about 10 billion years ago. But it turns out if that happens, it would have had to cross the 3-to-1 resonance with the close-in planet. And that kind of resonance crossing usually leads to capture, such that the planets should be in resonance now. But they're not in resonance now, so they probably never did cross the 3-to-1 resonance. And so we played around with this, and there was actually one other solution where planet B moved out a bit and planet C also moved out. But in that case, their initial orbits, which had much higher eccentricities, would have been unstable, and that doesn't work either, because if they were unstable, then they wouldn't be around now. And so this was kind of our best fit of what happened in the past to the orbits of these two planets. So planet C probably moved in maybe 0.01, 0.02 AU or so. It didn't ever, we think, ever start in the habitable zone, but it started a bit closer to being habitable. And kind of a neat thing about this is that using these constraints of crossing resonances and stability, you can constrain actually the interior structure of these planets to some degree in terms of how much energy is dissipated by tides during this process. And so that's kind of cool.
Does the luminosity of small stars change as much as large stars do?
Oh, you mean on the main sequence? That on the main sequence luminosity changes more slowly. So, the sun's, 30 or 50% brighter now than it was 4.5 billion years ago. That effect is smaller for low-mass stars, but it turns out that low-mass stars actually take longer to reach the main sequence. So early on in their evolution, their luminosity decreases much more slowly. So, I'm kind of running out of time, so I'll skip this. But what we did is you can kind of generalize this idea for more, try to apply it to general systems of planets around low-mass stars. But I won't go in that now. So just let me jump to the conclusions. I got 3 conclusions for you. First of all, the Illumina 26 story. Depending on the orbit of planets within their kind of birth cluster, you get more or less Illumina 26, which affects, in the end, the water content of planets like Earth. In hot Jupiter systems, you probably also have these hot Earth, these close-in Earth-like planets, which might be detectable with transits or transit timing, and you might form, very water-rich ocean planets behind them. And lastly, for low-mass stars, models suggest that you can't form very massive planets in situ in the habitable zone, but we see them. So how did they get there? That's a whole other question. And then tides also have an important effect on the lifetime of planets in the habitable zone. So that's all I got for you. Thanks for coming.
Any questions? Erica.
Going back to the thing with aluminum 26, when you showed the little cartoon before, you were talking about it being injected. It looks as though you're claiming that the disk would have already formed. Because I know previously it was thought that it was injected during a supernova that would have caused the disk to form. So you're saying that the supernova occurred after the disk was formed?
Yeah, there's evidence for the injection happening late. So it probably happened after things actually started to form. So it probably happened when there was already a disk present rather than causing the disk to form.
With the hot Jupiters, what are the chances for the development of a water-rich moon? Are those good candidates for...
Oh, of the giant planet as it moves in?
Yes.
That one? Okay. Well, there's a few different effects that go on. As a giant planet migrates inward, if it has a moon orbiting prograde, that moon actually moves inward a little bit. That's one effect. Another thing that as it's migrating through all this rocky stuff, which is getting hurled past the giant planet. In some cases, you could have a relatively large body, larger than the moons. The moons themselves actually getting close and maybe disrupting them. And then also, when it's very close in, it's hard for a large moon to survive. Actually, for tidal effects, which go in the opposite sense in certain cases, depending on the rotation rates. And so, very close in giant planets probably don't have large moons. They can have them outside maybe half an AU or so. You can have a large moon, but inside that, it's unlikely.
Lauren.
Are there hot Jupiter migration scenarios that take place later in time, i.e. after terrestrial planets would have actually formed, or do they actually require the presence of gas in the disk in order to migrate?
In general, it's thought to happen because of interactions between the gas and the giant planets. Some people have proposed the idea that you could have a large amount of migration by scattering small bodies, like in the outer solar system. But to have that happen, to move a planet really far inward, is tricky because the accretion time is such that you're not going to have a whole population of small bodies to scatter. You'll have a few large ones. And getting that to happen in a nice smooth way where you end up always going the same direction is not so clear. So in general, it's thought to happen. Migration is thought to happen when you still have the gas around.
We'll cut to some questions from the ether first and then come back.
So, Payne Tian, you have a question?
Yes, Sean, great talk.
Hey, how's it going?
My question is on the ocean planets, in the migrated giant planet scenario. After the giant planet migrate to very close to their stars, they seem to have ocean planets formed with large eccentricities, if I'm reading a plot correctly. And the disk probably has already dissipated by that time, by the end of the migration. How can those ocean planets reduce their eccentricity, if that's possible? Thank you.
Okay, so what we think is going on in the story is the giant planet forms in the gas disk, then migrates inward because of the gaseous disk kind of pushing it in some sense. And then one thing that's not really understood is how migration stops. And that's kind of a key part to your question, because one idea is that migration stops because migration is happening as the disk is dissipating. And so once the amount of mass in the disk is less than the amount of mass in the planet, then the disk can't really push the planet around anymore. So that's one idea. In that case, there's not that much gas left when migration ends. And so there's less of this orbital damping from the gas, on these protoplanets that were scattered outward, I mean. So we ran some cases in that case where you have very little gas left. And it turns out you can still form planets exterior to the hot Jupiters. The time scale for formation is actually quite a bit longer because the gas has a nice effect of reducing the inclinations as well. And so you increase the cross-section for collisions. And so it's easier to form this next generation of planets if you have a good amount of gas left after migration, but it's not required for that to happen.
Penn State has some questions.
Yes, I had a question about the aluminum-26 effect on the waterline. I might have missed this, but was this because of the radioactive decay that's forcing the waterline to change?
Yeah, it's kind of a race between the decaying aluminum-26 and the formation of larger bodies. Basically, if you form large bodies very quickly, you incorporate the aluminum-26 and it kind of heats up the whole thing. If these larger bodies form very slowly, then the aluminum-26 can actually get rid of most of its heat without heating up that much material. And so it's kind of a combination of accretion time scale of things that are at least about a kilometer in size versus the decay of the aluminum-26. And if things form within maybe 10 or 20 million years, then they feel the aluminum-26, but if they form very slowly, they don't. And so basically when they feel it, that means that they're driving off the water. That's what I mean.
Sean, I also have a question here. This is the other Sean at Penn State. Great talk, by the way. The one question I had was, how much chemistry information can you get out of your models? Do you just have sort of a density number and a water versus rock content, or can you get into more detail than that for those of us that may want to, find out what some of these planets end up looking like after they've formed?
Yeah, right now what we do is very simple. All we do is we keep track of, we have a rough initial distribution of iron versus rock and a rough initial distribution of, where the water is. And then in the end we kind of combine the different ingredients and say, what do you end up with? And it's really hard to take into account depletion. Nick Cabe and I are looking right now at trying to take into account depletion of water during these impacts in a somewhat consistent way. But it's a tricky thing to do. And we're kind of lacking in data on both ends in terms of, where are the condensation lines for different elements that are important, and also exactly what's the composition of the Earth anyway that we're trying to match in terms of how the Earth formed. And we're actually lacking in data on both ends to really reproduce that. And so if anyone wants to think about this in more detail, let me know, because it's very interesting, but it's not an easy thing.
Thanks, great talk. Those are all the questions we have.
Okay.
Rich. What assumptions do you make about the clouds and the albedo relative to the wavelength of the star?
The clouds for the habitable zone thing? We grabbed that right out of a paper, it's basically the Jim Cassing et al. Type model. And clouds can have certain effects, basically heating effects or cooling effects depending on the properties of the clouds and such. And so what we were looking at there was kind of, the reason we threw that in there is the part that I didn't really talk about was showing that in some cases you could have a planet form in the region where you don't need clouds, where we're pretty confident that if a planet is at that zone, it's got a good chance to be inhabitable. And we were looking at the time it would take for tides to affect the orbit of that planet such that it would move inside the 50% cloud zone, which corresponds more or less to the orbit of Venus or so. And so we were looking at that in terms of going from somewhere that was pretty certain to be habitable to somewhere that was kind of doubtful to be habitable. I didn't end up talking about that much, but the details of that are really right out of Jim Cassing's type models.
No.
When you're modeling the accumulation of aluminum-26 in the cluster environment, are you assuming then that the cluster's unbound and that as soon as the gas dissipates, nothing's holding the stars together?
Yeah, so we did it, let's see. When Eric did these first, he actually screwed them up. But anyhow, we did them again, they were right. And so what we do is it's consistent in that you have a cluster of these 9,000 stars that, with a dissipating gas potential retaining them. And at the end, there's 3 stars that are massive that are injecting the radioactive stuff into disks. And by the end of the integration, which is 10 million years, the cluster is dispersed completely.
Okay. Because that's
it's like the embedded cluster idea rather than leaving behind an open cluster.
Right. Yeah. So the question was going to be, has anybody looked at if the cluster's a bound cluster, like in the minority situation?
No, we haven't looked at that yet. We started off just looking at kind of the most likely outcome, and actually the case where Eric screwed it up was leaving behind a bound cluster.
Oh, okay.
And so it was kind of interesting. The distribution of aluminum-26 for those runs, which were not what we thought they were at first, was actually kind of interesting. It was a little different. It was bimodal actually, instead of having that one big peak, based on which clusters actually stayed around in the cluster and which stars stayed around the cluster and which ones didn't. But
Ava.
Yes, all that aluminum-26 retains in kind of pre-solar grains, or could you actually use it to get relative ages of different grains in the meteorites?
So you're asking whether aluminum-26 can actually use to date individual things?
Just relatively, to get a relative age, like to see which is the first grain that condensed.
And so, for example, like the reason I know it's done to some degree to look at, you look at the ages of lots of these different individual inclusions inside meteorites, and you can see difference in ages, for example, between the oldest ones, which are called calcium aluminum inclusions, the CAIs, and ones that have aluminum-26, for example. And that kind of method is how it's been figured out that there was a later injection of aluminum-26 that happened after the formation of the CAIs. In terms of looking at the details of individual grains, I think these guys in general don't trust necessarily each grain, but try to get a statistical sample to try to see what's really going on. I don't know too much about the details of how they do.
Donald.
Well, what's actually measured is the excess magnesium 26, what's the decay of aluminum 26. And the typical value is 5 times 10 to the 12 ratio of aluminum 26. Decay product to aluminum 27. But there are variations. There are systematic deviations between common rules and calcium inclusions. Also, some things that don't show excesses. And that was the implication that they were made before this stuff was salted in the solar system. But that's how the chronology of the solar system was determined, from aluminum 26 and 96.
Okay, well, Sean is going to be around all week, I believe. What?
I think there's another question.
Oh, is it?
Okay.
And Ken, you have another question?
Oh, yes. So this is related to the ground scenario of how to bring water to terrestrial-like planets. Did you see that it took about 20 to 30 million years for water to reach these planets? Is that a typical time scale? And a related question is, the water presumably are brought in by the planetesimals, and did anybody look at how the water on those these targets evolve in time, if it's really 20, 30 million years time scale? Thank you.
Okay, so in terms of how long it takes for this kind of mixing between zones to happen, and for water-rich stuff to end up at 1 AU, that can vary a bit from simulation to simulation. It's typically not immediate. There's some delay, just to have eccentricity stirred up enough to really mix different zones. So it's typically a delay of maybe 10, 20 million years. So that part we think is really happening, that delay. But the process continues, since from when it happens until till the ending, till you finally kind of clear out the asteroid belt and you clear out all the rest of this stuff. And so it can extend to maybe 50 or 100 million years or so in terms of small bodies still impacting the Earth. There's a constraint that the last large impact on the Earth didn't happen later than maybe 30 or 50 million years or so. In terms of water retention on the Earth, the key factors are how fast the impact is happening, and also what's going on, I guess, a bit of what's going on the planet. And so maybe if impacts happen later, the planet's cooled off a bit, maybe it's a bit easier to retain water. I think that might have been what you're getting at. Is that right?
Yeah, that's certainly one important aspect of the retention problem. The other part is how can water remain on those smaller objects at the first place?
Yeah, that's a good question of whether if bodies have eccentric orbits that take them very close to the sun, for a long time before they end up impacting the Earth, will they retain much of their volatiles? Comets take 10 or 100 passes close to the sun to break apart. So maybe they have 10 or 100 orbits before they need to collide with something before they lose most of their water. We're not sure. That hasn't really been looked at in much detail. That's just one uncertainty, and there's already plenty of uncertainty in terms of how much is retained in large and small collisions, and so I don't think anyone's...
Thank you.
Okay, well, Sean will be around all week if you want to speak to him further.
Yep.
Leaving Friday, I believe.
Yeah, Friday morning.
Friday morning. So take the opportunity to pick his brain. And thank you very much for the talk, Sean.